send it out. I found the email. So if you look back at your email, you should be able to find it. This list that I have is called the umbrella list. UMB stands for umbrella list, and it actually is the list for all the sections of 604 that I have. So if you can't find your questionnaire, I will send it again. But a few of you have returned it, but many of you did not return it. And I appreciate it if you can return the questionnaire, so that I can know your background better and know where you come from. I think most of you are EE major or ECE majors, but some of you might not be. Okay. In that case, I might need to fill in the blanks regarding your background. Okay, like somebody does not know what an impulse response is because he came from a mathematics background. And there are a few of you taking this course from nuclear engineering, mechanical engineering. So it would be good if I know your background better, so that if I say something that is out of the ordinary, that a non-EC major might not know. So I'll try to elaborate on that. Let me make a roll call. Alaina Atanasio. Yes. Muna Avajan. Yes. Saleh Masama. Ara Chanka. Yes. Colin Brown. Yes. Yu Heng Chen. Yes. Travis Crawford. Oh yeah, here today. Great. No, you will not. No. Otherwise, I wouldn't have noticed. Maybe the one key. How happened? The Dongku. Bin. Thomas Canal. Christopher Lackney. Okay. Yu Peng Lee. Okay. Geoffrey Marquez Sanchez, Vera Maranivo, Logan Malikan, yes. Sophie Thompson Kane, yes. Ryan Schneider, yes. What's the name?
Brandon Triplett.
Okay.
Can you say it? Or did I?
You just come in time, okay? Booking time. Yes, Brandon Triplett. Is you here? Hao Shen Wang. Good. Ye Wang. Good. Yue Hua Wu. Good. Yi Yang. Good. Joseph Zulo. Okay. Okay, let's get started. Are there any questions before we get started? If not, then let's get rolling then. So we have talked about uniqueness, okay? And we say that uniqueness is possible if you have some loss in the system, and I probably did not elaborate that quite well. Let me go back to elaborating that again. Okay, that if I have some loss in the system, then uniqueness is guaranteed. So we talked about uniqueness theorem the last time. And then we end up with this equation after taking the different solution. Okay, we assume that we have two possible solutions and take the difference, and found that the difference of these two possible solutions would satisfy this equation at the bottom. Is quite straightforward. So that where delta E is the difference between the two competing solutions. And you notice that the different solution does not have a source term on the right-hand side. And then we went and did some vector algebra, saying that if I were to take the divergence of this, then I will get this thing over here. And then I can replace curl of delta E from the previous slide and end up with this equation. Okay, this equation, if I can make the left-hand side go to 0, then I'm halfway there. Okay, if I can make the left-hand side go to 0, perhaps everything on the right-hand side should also be 0 as well. However, you can make the left-hand side going to 0 by imposing boundary conditions. For instance, if EA and EB satisfy the same boundary condition, I have two competing solutions, EA and EB. And if they satisfy the same boundary conditions, then delta E is equal to 0 on F. Similarly, delta H is equal to 0 on F. Can you see that? That if two competing solutions have the same boundary conditions, then the difference on the boundary should be 0. By using this fact, you can use the scalar triple product and so on. It causes the left-hand side to go to 0. Okay, it causes the left-hand side to go to 0. And if the left-hand side is 0, would that make delta H equal to 0? Our goal is to prove delta H equal to 0. Delta E equal to 0. If we can prove this in 0 inside the cavity, inside the region B everywhere, then uniqueness is guaranteed because these two solutions are actually the same solution. But when would they be equal to each other? So we go about studying this equation, and let me go to the new slide for today then. So there are manners or ways that you can make the different solutions go to 0 if you were to introduce small amounts of loss. Okay, let's assume that you can make the left-hand side go to 0. And that is not good enough yet, because it doesn't guarantee that the right-hand side is equal to 0, because you will end up with the equation that says that something like this. But let's look at the simple case. Let's look at a simple case for isotropic medium. Okay, in that case, we will make mu becomes a scalar number. Sorry, we make epsilon becomes a scalar number as well. And then that equation that I showed you in the previous slide simplifies. It simplifies to one that looks something like this. That the previous, let me write down the previous equation that I had before. We were able to make the left-hand side go to 0. Then on the right-hand side, we are left with this ugly-looking integral that most of you probably don't like. Okay. But if you have to study electromagnetics, that is what you have to grapple with. Okay. So we are going to make mu and epsilon simple. And we are going to make mu to be a complex number so that it has the real part and a small imaginary part. And then we're going to do the same to epsilon. It's going to have a real part plus a small imaginary part. So you plug this with scalar numbers now. Okay. You'll find that now if you were to take the real part of this equation, there will be this equation, it will consist of two parts, the real part and the imaginary part. Okay, I don't know if you can see the algebra quite well. So if you plug in mu to be a complex number, you can separate the above equation into real part and the imaginary part. Let's assume that when you take the real part, or when you take the imaginary part of this equation, you will only pick up the mu prime and the epsilon prime term. Can you see that? If you were to take the imaginary part of this equation, because of this imaginary term going everywhere, okay, so you have two terms that would still not guarantee the different solution to be zero. However, if you were to take the imaginary part of that equation, okay, plug it in and take the imaginary part, you notice that delta H star dot mu times delta H would be a real number if you only have mu prime, and then the second will also have a real number. The difference is that the second term has an epsilon conjugate on here. And if you do things correctly, so what you find is that you end up with the equation where you only have the imaginary part. Okay, if you take the imaginary part of this equation, you will have something like mu double prime delta H star dot delta H. And then if you take the imaginary part of the second term, because of the complex conjugation, you have epsilon double prime delta E conjugate. Okay. So there's a big difference here. There was usually a difference in the sign for the magnetic field and the electric field. But after taking this imaginary part, assuming a small loss, you now have both terms. Both terms are negative definite. Can you see that? Delta H star is positive definite. This term here is just delta H star. This term here is just delta E star. And then this thing is always less than zero. If delta H is not equal to zero, if delta E is not equal to zero, okay, that is always less than zero. So this allows you to argue that if I have a small amount of loss, this equation cannot be satisfied. That's it. For delta H and delta E going to zero. Can you see the argument? When I have a little bit of loss into the system, this equation cannot be satisfied unless this is equal to zero and this is equal to zero. Can you see that? So if those two terms are equal to zero always, in the integrand, it says that the two solutions EA and EB are always equal to each other. Uniqueness will be guaranteed. So it is a very peculiar thing. It says that uniqueness cannot be guaranteed unless you introduce a little bit of loss. If the system has no loss, you cannot be guaranteed uniqueness. Okay. So you can generalize this to an isotropic case is done in the lecture notes. Okay, so I here just illustrate a simple case where the medium is isotropic. So the math is a lot simpler, but if you can go through the math for the anisotropic case, the same statement holds true. Okay, so what it says is that if you have loss, okay, uniqueness is guaranteed. So how can we rationalize this using all the mathematical knowledge and all the physical knowledge that we have so far? Okay, let me try to motivate this using some hindsight from linear algebra. Linear algebra that most of you have taken a course in say that if I have this equation, it will have a unique solution if A is non-singular. If A is non-singular, you can invert this matrix system and find X. Okay. However, if A is singular, you cannot find its inverse. And A would be singular when it has a null-space solution. Null-space solution is considered to be the solution that exists when there's no driving term. B is a driving term. It's a forcing term of the system. So when the driving term is 0, and you still have a solution, that solution is called it has different names in different communities. The mathematicians call it the homogeneous solution. The physicist calls it the resonance solution, or the resonance solution, or the natural solution. They mean the same thing. All the three ways of saying it mean the same thing. Solution without the driving term. So when an equation has a resonance solution or a natural solution, the system is not unique. Okay, you can understand this because if this is the case, then given any solution that you have found, you can always add a null-space solution to it, and this equation will always be satisfied. When we look at this equation, the driving term, we found that the difference solution is a solution to a homogeneous equation with no source term. If you go back and look, the equations for the different solution has no driving term. So if a set of equations has no driving terms, when would it ever have a non-zero solution? When you hit the resonance of the system. Okay, I'll give you a very good example that, say if I have a tank circuit, it has a resonance, and you know that I can drive this problem with a voltage source, for instance. And if I happen to drive this LC tank circuit as a resonance solution of the tank circuit, do I need a voltage source to give rise to a non-zero solution? No, right? So if I were to take the voltage source away, I have this problem. And when would this problem have a non-trivial solution? It's an undergraduate ECE problem. When would this LC tank circuit have a non-trivial solution? You know?
After the energy loss spent after fall from the tank.
No, that's not what I'm looking for. Maybe somebody has a great idea. Very good. At the resonance frequency of the LC tank circuit, you don't need a driving term anymore. There'll be natural solutions for the current to slosh back and forth. Okay, so that is exactly in mathematics we call a Downspace solution. Okay, when that happens, the solution is not unique. That means that if you were to solve this LC tank circuit problem with an ODE, that some of you might have gone through when you did undergraduate ECE courses, you convert the LC tank circuit into an ODE and then solve for the solution. And you'll find that there's a voltage source on the right-hand side, and when you switch the voltage source off and ask if there's still a solution, that would be the resonance solution. Okay. It's the same kind of situation, and you can actually look at this from a different viewpoint, from a signal processing viewpoint. That if you have an LC tank circuit, a very simple circuit problem, you can also solve this problem in terms of linear system theory. Okay, you find a transfer function. And for instance, if I were to connect this to signal processing, what are you seeing there? So let's think of this tank circuit again. Okay, and then you have a current I, a voltage B. You find that the relationship between I and B is given by this, the transfer function, which is I, which is my input, my voltage must output. So I can think of I as my input and then write a Y omega. Y omega is just the admittance of this circuit. Okay, you can work that out quite easily. And then when you look at this problem from a signal processing viewpoint, this circuit will not have a unique solution when the transfer function has poles. If the transfer function has poles, we cannot perform the Fourier inverse transform. If you look at it from a signal processing viewpoint, just like the top picture over there. So when the system is lossless, we have resonance solutions that live in the real omega axis. And this allows you to use Fourier transform technique or phasor technique to solve this problem. However, if you were to introduce an infinitesimal amount of loss, the poles will be forced to move away from the real axis. Can you see that? Okay. When you introduce an infinitesimal amount of loss in a linear system, you don't have a natural solution that is anharmonic anymore. The solution that is natural, solution without a driving force, has to be decaying signal force. Okay, they have to be decaying signal force with an exponential decay. I hope you can see this from the circuit theory course, and then all the poles of the system will move to the complex plane. Now, if you do phasor analysis, you always keep omega to be real. And even if you do Fourier transform analysis, the omega is always on the real axis in order for you to use Fourier transform. Then the problem is uniquely defined. Okay, any questions on this? So how does this kind of non-uniqueness manifest itself in solving a boundary value problem? Well, it actually can be a nuisance. Can be a nuisance, which means that if I have a volume V, if I put a source J in there, and then I put boundary conditions on the wall of this region V, and if this medium is lossless, I potentially can have non-unique solutions quite easily. Okay, what causes the solutions to be non-unique? Now you know the physical reason. The solution is non-unique because they are resonant modes in the system. Solutions that can exist without the need for a driving point. In the language of matrix algebra, those with the Downspace solution. In the language of mathematics will be the homogeneous solution. The language of physicists will be the natural or the resonant solution. They're all the same thing. Okay. So do you know that I hope some of you can appreciate this fact that if you have a cavity, you might have taken a course in undergraduate EM before. You have a number of modes in this cavity. If you make the cavity bigger and bigger, what happens to the number of modes in the cavity? Anybody?
There's more possible modes.
There are more and more possible modes again.
Yeah.
The whole Fourier space will be replete with modes of the system, which means that if you were to solve a simple cavity problem, which many of you have done, say if you were to have a rectangular cavity, this is right today. I don't know why I cannot draw. I cannot draw now. It always confuses me. This one can draw. I can never understand technology. Okay, so I bring 5 pens for me. One of them will work. Okay, so that's how I understand technology. Play the number again. One of them will work. Okay. So if I have a cavity and something that you might have studied in the undergraduate course, the resonance frequency of this thing is given by this equation, which is beta x squared plus beta y squared plus beta z squared. And if you work out the beta x, beta y, and beta z for this problem would be n pi over n squared plus n pi over d squared plus p pi over d squared. Okay. So you can see that as you make the A, B, and D very large in this cavity, the number of modes that you have becomes very, very large. Okay. So if you were to plot this thing in the mode space, okay, there will be modes in the rectilinear space. In all the spaces, we'll find a mode according to this formula. This will be like beta x, beta y, beta z. Okay, and then you have this picture that is very nicely drawn in many textbooks, much better than my picture. Okay, and you'll find that those modes are everywhere in this beta x, beta y, and beta z space. And the spacings between these modes become smaller and smaller as A, B, and D becomes larger. Have you seen this kind of picture before? How many of you do not have a course in undergraduate electromagnetics? Because all of you do wonderful. Okay, so I'm not talking above your head or over your head. Okay, so as you make the cavity larger and larger, this space in the beta x, beta y, beta z space, sometimes we call it the momentum space or the reciprocal space, will be replete with modes. And if you were to pick an operating frequency, most likely than not, you will hit the resonant frequency of the structure. Okay, you will hit the resonant frequency of the structure, which means that if the cavity becomes bigger and bigger, the chance of you getting a unique solution inside the cavity is almost zero. Can you see that? But unfortunately, the space you live in is the very, very big cavity. So if we were to solve Maxwell's equation, in this huge cavity that we're living in, this cavity will be replete with resonant modes, and there's almost no unique solution. So what can we do to get rid of non-uniqueness? We just learned in the previous lecture, to get a unique solution, you must have an additional condition to the wave equation of the Maxwell's equation. What was that additional condition that we have to apply? Yes. Not boundary condition. Boundary condition itself doesn't do it. You need something else. Okay, boundary condition gives you the modes, and as we said before, even with the boundary condition, you get the natural solutions of the resonant solutions. They exist. Yes. Very good. You put in a little bit of loss, then the time harmonic solution cannot exist anymore. Can you see that? All the natural solutions that you have in the lossy cavity have to be non-time harmonic. They have to be decay exponential. And if you are operating on the real axis, a real omega axis, you will never hit a resonant solution if all the resonant solutions are decay sinusoid. Okay. So one way to get the solution to be unique is to introduce a little bit of loss. You can only have decaying solutions. Another way of imposing loss in an open space is called the radiation condition. You let the wave radiate to infinity and never come back. If you have a situation where you can let, say, okay, you can let a boundary value problem, and then you let this boundary go to infinity, And if you have a source here, and you let the field radiate to infinity and never come back, that is another way of saying that I'm making the system law. I can never have a time harmonic solution in such a system. Then the solution is always unique. Okay, the solution is always unique. And some people call this a Summerfield radiation condition. Are there any questions as to how you can make the solution unique in solving electromagnetics problems? Okay, if not, let's move on to another interesting topic, which is reciprocity. Okay, we go to the math derivation of reciprocity and so on. And well, I like to quote sayings from Confucius and the Holy Book on reciprocity that you can see from here that I'm referring to. And this is like saying that if you do something harmful to others, others will do things that are harmful to you. And this was uttered by Confucius, who lived around, how many BC did he live? 200? No, he lived quite long ago. A few hundred BC, okay, maybe 400 BC. And then this is also said in the Holy Bible. I need to look up Matthew 7.12. Look, what is that? 6:31. If you see others as you would have them do unto you, or do not do unto others as you want others to do unto you. Okay. So, but in electromagnetics, this can be written down precisely in mathematical terms. You're laughing. So why is it so funny?
This idea that electromagnetics is like the precise version of dipole modification.
Okay, good. Good, very good. Well, since I study electromagnetics for so long, it actually is a gift of God. If you understand everything in electromagnetics, you find it so beautiful. Okay. So let's prove reciprocity theorem. So for this, we have to do a Gedanken experiment. You know what a Gedanken experiment is, right? It's a German word for thought experiment. In the first experiment, I assume that I have a complicated structure. I describe it with mu and epsilon. This is a very simple picture, but this mu and epsilon can represent a mountain range. You can represent an antenna tower. You can represent microchip circuits inside a computer circuit. So for simplicity, I just say that mu and epsilon represents everything that I have in this world. But in order for them to be reciprocal, you'll find that mu and epsilon has to be of a certain form, which I'm going to derive. So I do experiment 1. I put sources J1 and N1 and turn off the second batch of sources J2 and M2. Then I come back to the same geometry, the same terrain, the same computer chip circuit, the same antenna tower. I turn on the source J2 and M2. The second time around, I turn off J1 and N1. So when I did experiment 1, I have field E1 and H1 all over the place, including inside the complicated structure. And the same thing when I did experiment 2, I get E2 and H2 everywhere, permeating all of space, including inside the very complex structure. But I know that these two fields satisfy Maxwell's equations. Okay, so they satisfy Maxwell's equations. So I can derive something about the relationship between them. Okay, so in experiment 1, I don't know why it's so thick now. Maybe something got. Okay, let me try this one. This works. This works. So I try experiment 1. I know that this equation must be satisfied by experiment 1, which is that now actually it's drawing for me without me touching the surface. It's no good. Let me try another pen. Experiment 1, okay. Curl of E1 must be I omega mu. I did not change the geometry, so mu remains the same. Okay. I will have this equation for experiment 1. And then curl of H1 is equal to, I should use J. Okay, I should use J since I'm talking electrical engineering right now, not optics. I have the first 2 of the 4 Maxwell's equations, as I said before, for electrodynamics, they are okay because the third and the fourth are derivable from the first 2. So experiment 1 will give me these equations. Experiment 2, same geometry. Okay. But then I would just replace everything with 2, subscript 2. But mu did not change because it did not change the geometry. I changed my source, and then I would have curl of H2 with J omega epsilon E2 plus J2. Okay, so these 2 experiments are indicated by these equations. And the next thing I need to do then is to see what kind of theorem I can derive from these 2 equations. Okay, so this is hindsight. I wouldn't have imagined this nice derivation. It's all done by our predecessors, and they must have some hindsight somewhere. Okay, you take this equation and dot multiply with H2. Okay, and you take this equation and dot multiply with H1. And you do the same thing to the other equations. Okay, you do the same thing to the other equations. Let me see if I do it correctly. H1, and then this one you will have E1 dot. And then you will have E2 dot with this equation. So things are getting confusing. But the goal here is that, can I come up with a nice equation when I subtract this equation? Okay, you'll see that the way things are structured, H1, H2, some of the terms are cancelled. I don't know if you can see that well, but on the left-hand side, you subtract them. I will have H2 dot curl of E1 on the left-hand side, and then you subtract them, it would be something like if I take this equation and subtract this equation, it will be E1 dot curl of H2. Okay, if I take this equation and subtract this equation from it, I will have this thing. And then on the right-hand side, I should have equal to minus J omega H2 dot mu dot H1 minus H2 dot M1 on the right-hand side. Okay, that's from the first term, and then from the second term, the right-hand side, I will have minus J omega E1 dot epsilon dot E2 minus E1 dot J2. Okay. And you notice that this equation on the left can be written succinctly using the product rule. Okay, using the product rule, that is just equal to the divergence of E1 cross H2. Okay, the right-hand side, the left-hand side can be written as such. And then you can do the same thing again. U2 cross H1 now. Okay, and then obtain another equation very similar to the first equation, except that you just swap 1 and 2. Okay, just swap 1 and 2 on the right-hand side. And the right-hand side will just become H1 dot M2, and then minus J omega E2 dot epsilon dot E1 minus E2 dot J1. Okay, can you see that? Those equations are just that. And now if I subtract these two equations, I don't know if you see this. This term is very similar to this term. Okay, and this term is very similar to that term. Okay, but they are all scalars, aren't they? You have a vector multiplied by a matrix times a vector. They are scalars. When would that term be equal to this other term? When would this be equal to that? And when I subtract them, they will cancel each other. What is the condition on mu? Anybody? Yes, Sanchez? When would they be the same? If I subtract these two equations, I want that the terms that I have double underlines to cancel each other. When would they cancel each other exactly? Something you have to get some knowledge of. Yes. Yes, mu is a symmetric matrix. If mu is a symmetric tensor, and the two are the same, right? You know, matrix algebra. Matrix algebra says that if you have this H2 dot mu dot H1, if you take the transpose of this, it will be just H1 dot mu transpose dot H2. Okay, you remember from your matrix algebra, this is true. And I hope you still remember your matrix algebra. So those terms are actually the same if mu is a symmetric tensor. So, but you require that mu equal to mu transpose, which is the definition of symmetric tensor. Okay. The H terms are cancelled, the E terms are also cancelled if you go and convince yourself. And finally, the right-hand side all cancel each other. And you only have the current terms left. Okay, so what happens is that you have something much simpler on the right-hand side now. So you take the difference of these two, you end up with this identity. E1 cross H2 minus E2 cross H1 is equal to minus H2 dot M1 minus E1 dot J2 plus H1 dot M2 plus E2 dot J1. Okay, only the current terms are left. The other terms all cancel each other. So this is a much simplified equation that we have now. And on the left-hand side, it is the divergence of two terms, the difference of two terms. Okay. So when you see a divergence what would make you jump with joy, or what would come to your mind when you see a divergence? What is the next mathematical trick you would use, or what should you do from this point onwards? Yes. Very good. Not closed surface, integrate over a volume with the closed surface. Okay. So if I integrate the left hand side over a volume and then use the Gauss divergence theorem, it can be converted into a surface integral and only have a surface integral left. On the right hand side, I cannot do anything, it will remain to be a volume integral. Okay. Very good, Logan. So let me do this now. And this derivation is predicated on this fact that I only have symmetric tensors in my problem. Okay. So now if I integrate this over two cases, case one, I integrated over a volume with a surface that does not contain the current. If the volume does not contain the current, then this integral on the right-hand side will go to 0, right? There's no current on the left-hand side. Only have this. So if I have only integration over this case over here, I only have the left-hand side left, okay, which is a surface integral by using Gauss divergence theorem minus E2 cross H1 over that closed surface. That has to be 0. It says that if I have two different solutions, E1 H1 and E2 H2, that solution has to satisfy this theorem. This is called the Lorentz reciprocity theorem. It is integration over that surface F containing the volume V, and this V does not contain any source. Okay, but you can do other things as well. To me, you can come up with another reciprocity theorem, which is quite interesting. That is now, second time around, you integrate V over a volume V that contains the current now. Then the right-hand side will not be 0 anymore. You pick up the right-hand side. You still have the left-hand side. And you end up with another theorem. That theorem would say something like this, that if you remember the equation that I have, left-hand side remains the same, it's a surface integral, and then it would be E1 cross H2 minus E2 cross H1 dot is a surface integral. You will have this thing, but the right-hand side would be something quite interesting. It's a volume integral, okay? I would not use this triple integral in the future. It will just be implied when you have a volume integral. So you have first this dot product minus E1 dot J2 plus H1 dot M2 plus E2 dot J1. Okay. So this is the surface S that you integrate over, and the volume V contains M and J. So I have all these terms on the right-hand side that I have to keep. However, you can make the surface integral go to 0. You can make the surface integral go to 0 by taking it to infinity. Okay. And the derivation is done in the lecture notes. Okay, I wouldn't derive that, but you can show that when you let the surface S go to infinity, this thing goes to 0, okay? One of the things that you have to remember is that you have a source, J. It produces a wave, okay? Are you familiar with the fact that this finite source will produce a wave that eventually looks like a spherical wave? You probably learned that from your undergraduate course. Okay, you have a finite size source. That finite size source produces a wave. The wave may not look like a spherical wave when you're close to it, but when you're far enough from it, it looks like a spherical wave. Okay, and if you have a spherical wave, what does it look like in a very, very far region away from the source? Yes. Yes. Somebody say something. Penguin, right? It will eventually look like a penguin. So if you go far enough away, okay, see if I draw this far away, the radius of curvature of the spherical wavefront becomes bigger and bigger, and that wavefront becomes like flat surface. And we have studied plane waves already because it's the simplest wave that we study. Spherical waves are slightly harder to study. Okay. So with plane waves, you already know that the K vector and the E and H are all orthogonal to each other. So you can see that if we have J and M, J1 and M1, actually we have two kinds of sources, J, M1, and then we did an experiment J2 and M2 also around an object, which is very complicated. And then we looked at the left integral, and you can show that the left integral actually becomes 0. Okay, it's rather difficult to show, but what you have is that you can show that so the left-hand side is proportional to E1 cross H2, right? For instance, if you were to perform this integration over a surface integral, E1 and H2 would essentially become like a plane when you're far enough from the source region. So if you have a finite source, J1, say J2, each of them produces a spherical wave. And you can think of them sharing the same beta vector or the K vector. Okay, these two are used interchangeably in this course. Can you see that when you're far enough, the K vectors are the same? In addition that your finite sources, if you go very, very far enough, they produce plane wave propagating in the same direction. They produce spherical waves that are slightly off center, but if you're far enough away, those plane waves are traveling the same direction. Okay, if you're not convinced, then I can draw a picture. If J1 produces a spherical wave with this beta vector, and J2 produces a spherical wave with this beta vector. And if you take the observation point far enough from the sources, beta 1 and beta 2 are going to be parallel to each other. When you see that, this is like a parallax theorem, right? They're going to be parallel to each other. And you can use this fact to simplify E1 cross H2 and show that this is going to be, if I assume that they're plane waves now, then H2 and E2 are related to each other by the K vector. Okay, beta 1, beta. They share the same beta, so let me just use one beta for them, cross E2. Okay, since they're plane wave, you can use the beta vector cross with E2 to get H2, and then you can use the double cross product. What formula would you use to evaluate the double cross product? Anybody? Very good. Back to the cat formula. If you do that, then you can evaluate it, and then you have this being equal to E1 beta dot E2 minus beta E1 dot E2. Okay, you can do the same for E2 cross H1. And then you blah, 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 go to the end. And then you just swap 1 and 2. Okay, what do you know about beta dot E? If you're far enough away from the source, beta dot E should be equal to, beta is a K vector, E is electric field, 0, okay? So the first two terms will be 0, okay? The only thing you have left is the second term. And you can see that they're equal to each other, right? Which means that if you have this integral that you have, okay, they will cancel each other eventually, giving rise to 0 on the left-hand side. But you have to really prove that they cancel each other. Saying that they go to 0 is not enough. Many students will make a mistake. Left-hand side will go to 0 because they go to the far field. E1 has to decay as 1 over R. H2 also has to decay as 1 over R. Agree? I don't know if you understand this from undergraduate electromagnetics course, that all these far fields decays as 1 over R. And then a student will argue that if it's E1 times H2, then it will decay as 1 over R squared. And then they will go to 0 at infinity. What is the fallacy with that argument? The fallacious argument, it does not go to 0 because of that. Because when you perform the left-hand integral, if you make the surface S bigger and bigger, how fast does the surface area of S grow? You grow as R squared too, right? So saying that it decays as 1 over R squared is not the quotient reason to say that it is 0. So you actually have to prove that the two terms cancel each other, which I just did, okay? So having proved this, then we have this very nice theorem, left-hand side is equal to 0. If I consider the case where S tends to infinity, then the reciprocity theorem becomes very nice. Okay, the reciprocity theorem says that, let me see if I written it up anywhere. It just involves the volume integral of the current source, E2 comma J1 minus H2 M1, okay, must be equal to, because I said the left-hand side equal to 0, and just equate those integrations. I don't know why it hesitates. My PPD slide is not responsive. When I write on it, it hesitates. That I don't understand. Only a computer scientist can understand that. Does anybody understand why the response time of my PPT slide is so slow? What is that? You think it's a pen? I have 5 pens here. I tried so many times, and none of them seem to work well. Okay, so this is the reciprocity theorem expressed in another way. This is called the reaction reciprocity theorem. Okay. And if there's no m, then you can write it very easily. It's just e2j1 minus h2m1. And usually these kind of integrals are written as inner products, mimicking what the mathematicians would do. So you say that this is the inner product between E and J. So you can also write this using mathematical notation in terms of inner product. Something is flashing getting away. The whole thing is not responding. My computer gets up. Going round in a circle, and I don't know why it does that. Back to Microsoft. My feedback is that you shouldn't let Bill Gates monopolize this field. You get very poor services, very poor software from him. Okay, I think it's working now. I hope, I pray that it's working. And that, so let's apply this to some real world problems. Let's assume that we have two antennas. The two antennas are rather complicated. For horns or different kinds of metal. And as long as the metal is made of reciprocal media, that is mu equal to mu transpose epsilon equal to epsilon transpose, reciprocity theorem should fall here. Okay, it doesn't matter how complicated the antenna is, as long as it is made of reciprocal media. Now, we assume that we have two ports in this communication system, J1 and J2 are very, very small dipole antennas. Okay, we assume that they're so small that they're much, much smaller than wavelength. And are you familiar with the fact that when something is very small compared to wavelength, you can replace electromagnetic theory with circuit theory? Okay, so near the ports of these two antennas, I can write circuit theory for them instead of using full electromagnetic theory. And you can think of the terrain as a very complicated circuit that you might learn in your undergraduate courses. It's a very, very complicated circuit. Okay, but it is still a linear system. Because it is a linear system, then I can write a matrix for this system and show that if I have J1, E1, I do this experiment. If I were to do the experiment, I will show that J2, comma E1, which is the simplified expression for the inner product for the reaction. Okay, so these two should be equal, and this is the reaction reciprocity theorem. And I assume that circuit theory holds true. Okay, that the whole structure that I had can be replaced by this simplified structure in terms of a box where my J1 and J2 are just ports, just currents at the two ports. And what I have in that white box there is everything that you like to put in there. And as long as the two ports are very small compared to wavelength, I can look at them with circuit theory. And if I look at them with circuit theory, then I know that there is a relationship between E1, V2, and Z11, Z12, Z21, Z22. Thinking of this as a two-port network. This relationship must hold true. Okay. Think of circuit theory as a subset of electromagnetic theory. And you can replace all the complicated stuff with circuits. And you probably learn from your undergraduate course, no matter how complicated the circuit is, if you have only two ports, this is a simple relationship between the two ports. Then what you can do is that you can do your Gedanken experiment again. In port 1, you turn on J1 and turn off J2. Okay, and then in the second experiment, you turn on J2 and turn off J1. Then you look at the field everywhere, and then D1 is due to the field. Let me see. So what you have is actually you have the fact that you can turn them on and off quite easily, and then Like if you do E1, comma J1 first, J2 for instance. If you calculate this quantity means that find the E1 okay, at the location of J2 when J1 is on, but J2 is off. So you have to do quite a bit of things. You have to run this here down to your mind. In calculating this one, we have to find E1. E1 is the electric field at the location of J2 when J1 is on. The J2 is not on. J2 is just here for this example. And this quantity should be equal to the other quantity. Okay, let me see if we can calculate this quantity first. Okay, so to calculate this quantity, I will have to perform this integral E2 dot J1. And to calculate this, essentially, I have to find the electric field at port 1. And in order to calculate this one, it should be E2J1. If I have to calculate this quantity, which is, I turn on the current J1 and find the field at port 2, and then calculate this quantity E2 comma J1. Okay, so this would be like you can put a current there, which you can put a current I1 there, and then you can calculate it, and it would be essentially the same as E dot dr over the length of the wire. Okay, and this will be E2 dr, and this is the case where you turn on J1 but left J2 off. Okay, and then this would be the, did I say it right? This essentially is the current, the voltage. Okay, voltage due to J2. This is E2 is due to J2, and it is the voltage here, which I call the open circuit voltage at port 1, because J1 is on. When you confirm when only J2 is on, J1 is turned off. So that voltage that I calculate here at port 1, this is done over port 1. Okay, is equal to the I1 okay, you have to think a little bit to understand it. But J1 was not there. J1 was off. This one of the issues is calculate this one. So this quantity is in the open circuit voltage of port 1. And then in order to get this quantity from the circuit equation, what I need to do then is actually to make I1 into 0, and then you just find the voltage V1, and I2 is turned on. So you can find that this thing is actually related with V1. Okay, I don't have time to go into it, but this thing is proportional to V1. if you go back to the equation and make one of the things equal to 0, then go back to surface theory, fill out the equation again, and do this experiment now. Surface theory works. You find that this thing has to be equal to that, and then to do the second experiment. The second experiment will be and this will be equal to each other. You'll find that Z12 will be equal to Z21. Something that you learned in circuit theory long ago. Let me never prove how to prove this from Z12 equals Z21. So I guess I'll stop here. I'll let you read the rest of the things in the lecture note. Any questions before I stop? Here is still landscaping. Okay, thank you. Thank you for coming.